Let's talk about capacitance. We've already talked before about parallel plate capacitors. Parallel plate capacitor has two plates. One where you can put on a positive charge plus Q, and one where you can put on a negative charge minus Q, and they're separated by distance d, and they each have an area A, which is represented by the circle of their area. My circle is a little big there. That's okay. The purpose of this is to store charge and store the energy in the charge. It depends on the potential difference delta VC across the capacitor. Now, we found before that delta VC was equal to QD over epsilon naught A before. Today, we're going to look at a new relationship, and this is going to look at the amount of charge stored in any sort of device that has an electric field. This quantity is called the capacitance. This is the ratio of the amount of charge stored to the amount of voltage required to store that amount of charge. That is the capacitance. The capacitance is measured in a unit called the farad. 1 farad is equal to a coulomb per volt. And normally, capacitances are very small, picofarads to microfarads. Let's do a simple calculation. Let's see how much charge could a 3.2 microfarad capacitor store if you had a potential difference, delta VC, of 1.5 volts. Well, we use our equation. We see that Q equals C times delta V. That's 3.2 microfarads times 1.5 volts. And we see 4.8 microcoulombs once we cancel our units. Okay. So, how do you charge a capacitor? A capacitor is charged by using some sort of potential source, such as a battery. You start off with two plates that are initially uncharged. Then you apply a battery across them. As the charge moves from the top plate to the bottom plate, the top plate becomes more negative. The battery pushes that charge onto the positive plate, which becomes more and more positive. Gradually, this is going to create a potential difference, delta VC, across the two plates. This is going to continue as long as delta VC is less than delta V battery. Eventually, delta VC will equal delta V battery. At this point, no more charges will move, and the charges will remain stationary here. A bunch of negative charges on the negative plate, a bunch of positive charges on the positive plate, and everything will remain in equilibrium like this. At this point, you can remove the battery, and the charges will just sit here, remaining like that, stored. The energy will be stored in that separation of charge until such time as you connect a new wire or a new circuit. Let's look again at a parallel plate capacitor and see if we can find out the equation for the capacitance. Well, we've got the answer right there, so that should be pretty straightforward. Well, we already looked at the equation that we had for delta VC. Remember that delta VC is equal to Q times D divided by epsilon naught A. Well, remember that the definition of capacitance is Q divided by delta VC. So we'll divide Q by QD divided by epsilon naught A. The Q's will cancel out, and we'll get exactly epsilon naught A divided by D, precisely as our equation already told us. So that's for a parallel plate capacitor. We see that the capacitance depends only upon the surface area of the plates. Each individual plate has the same area A, and the separation between them. Let's do an example. Let's suppose you wanted a capacitance of 1 times 10 to the minus 6 farads. So that is a moderately large capacitance, a microfarad. At least in an electronic circuit, that would be a moderately large capacitance. And you want to find this with a very large plate, a large plate that has a surface area of a meter squared. What is D? Well, we're going to need epsilon naught, our constant, our permittivity of free space. So that is 8.85 times 10 to the minus 12 coulombs squared per Newton meter squared. And we'll just calculate D. So first we'll solve algebraically. D is equal to epsilon naught A over C. And then we'll plug in our values. So 8.85 times 10 to the minus 12 coulombs squared over Newton meters squared times 1.00 meters squared divided by 1 times 10 to the minus 6 farads, a microfarad. That's going to give us, well, we have a 10 to the minus 6, which will cancel part of that, so that'll leave us 10 to the minus 6 there. That's just 1 meter squared there. And so this will leave us with 8.85 times 10 to the minus 6 meters. We didn't complete canceling out those units, but they should cancel out and give us proper SI units for distance. So this is 8.85 micrometers, so a very small distance. So a parallel plate capacitor by itself is a pretty inefficient way to create a capacitance. We need some way to make the capacitor more efficient. That way is called a dielectric. So you create a dielectric capacitance. So you create a capacitor with a dielectric by putting some sort of insulator in between the two sheets of the parallel plate capacitor. This creates an induced electric field inside the dielectric, which partially cancels the electric field. This partial cancellation of the electric field allows you to more easily store more charge for the same delta V. Well, if you're storing more charge for the same delta V across the two plates, you've got more capacitance. So, there's a bunch of different types of there's a bunch of different types of insulators, dielectrics, that we use. Vacuum is not a dielectric at all. So it has a dielectric constant of what we call 1. The dielectric constant is this. The dielectric constant is this value kappa. So kappa is equal to 1 for a vacuum and approximately equal to 1 for air, and is equal to a number greater than 1 for any insulators that we insert in between the two sheets of a parallel plate capacitor. So you can see a bunch of different values: Teflon, paper, Pyrex glass, strontium titanate. All of these will increase the capacitance by decreasing the strength of the electric field in between the plates. All right, so that's what there is to say about capacitors. There'll be problems on the homework about them. If you have any questions, come see me.